Welcome to the 3.4 notes video. Today we're going to talk about finding the derivatives of inverse trig functions. In order for a function to have an inverse, it needs to be one-to-one. Mathematically, that means for all y in the range of a function, there's only one x value in C in that domain of that function f, so that f of c equals y. A simpler way to say this is that the function's graph should pass the horizontal line test, which means that I want to be able to draw a horizontal line through the graph of the function and only intersect the graph of the function once. Now you can see that in this particular example, f of x is not one-to-one. It's not one-to-one because it fails the horizontal line test. There's two x values, a and b, that would give me the same y value, f of a, which is equal to f of b. So we don't want that. This graph here of this function indicates that this function y equals f of x does not have an inverse function. Now we have a problem with trig functions because they're periodic. Okay, they repeat themselves after a while, right? Sine, if you imagine the sine wave goes like this, and cosine's the same way, and even tangent has a repeating pattern. And so none of the trig functions on their own will pass the horizontal line test unless we limit the domain of the inverse function and the range of the inverse function, which is to say that the range of the inverse function would be the domain of the original function. Right? Because to find the inverse, you switch x's and y's around. And so the range of the inverse would be the domain of the original f of x. Okay? And you can see that for sine, we have to limit the domain, or what we can put into the sine function, as negative pi over 2 to pi over 2. Okay? Just a reminder on the unit circle, which I have down below, but I will get to that in just a second. If I want negative angles, remember I always start at the 3 o'clock position, and this is 0 degrees. And if I'm going negative, I'm going this direction, and then if I'm going positive, I'm going counterclockwise. And pi over 2 is 90 degrees, and so negative pi over 2 would be pi over, or 90 degrees in the opposite direction this way. So the domain, the inputs of sine, if we're going to use the inverse sine, or arc sine, is going to be between negative 90 and positive 90 degrees. And you can see that I've limited the cosine function between 0 and 180, or 0 and pi. And here are all the rest of the domain restrictions for each of the trig functions, provided that in some of these that you have y values that they cannot be. Now you'll notice in this table that I'm using the arc notation for most of these. And that's the most common on the AP exam, is you'll see arc, mostly because they want to avoid using the inverse notation like this. Right, because a lot of students still think that seeing a -1 in that position means it's the reciprocal. And I want to tell you right now that that is not the reciprocal of sine, or in other words, cosecant. All right, sine inverse is the same thing as saying the arc sine of that angle. Okay, and I should use x because that's what I used on the other side. All right. Here are the graph of those 6 inverse trig functions after you limit the domain of their original functions. And you can see that they all pass the horizontal line test so that they can have those inverse functions. And I just want to go through some review of how to find values of inverse trig functions. And I just need you to know that the input of this, we're inputting a value, and the answer that you get out of an inverse trig function is going to be some angle theta. So output is an angle. Trig functions output angles. And when I ask for the arc sine of -1/2, I'm asking for a triangle relationship that looks something like this. Remember that sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. These are the 3 basic trig ratios you should have learned before taking this course. And if I want the arc sine of -1/2, I'm asking what angle theta is going to give me an output of -1/2. Well, remember that sine is opposite over hypotenuse, and so the opposite should be -1 and the hypotenuse should be 2. And I'm asking what angle should get me a -1/2. Now that's why I put this unit circle here for your reference. I'm going, remember, between the angle values of -90 to positive 90 degrees, or that is negative pi over 2 to positive pi over 2. And I'm wondering, when is the sine -1/2? And remember that sine is always the y value, and cosine is always the x value, okay? So when is the y value -1/2 between negative pi over 2 and positive pi over 2? Hopefully you can see that right here. At 11 pi over 6, we get negative 1 over 2. Now 11 pi over 6 is assuming we went counterclockwise all the way around to get to that point. But instead, I'm going from 0 negatively, and so I need negative 1 pi over 6. Excuse me. So the theta in this case, that is the arc sine of negative 1/2, would have to be negative pi over 6, or negative 30 degrees. What is the arc cosine of 0? Well, the arc cosine of 0 would mean that the adjacent over the hypotenuse would be 0 over 1. And so theta would be here. And so what angle between 0 and pi would get me a cosine of 0? Remember, cosine is the horizontal component, so between 0 and pi, the cosine is 0 at pi over 2. That's the angle I want for this problem. So theta would equal pi over 2. In the third example, arctangent of square root of 3. Now square root of 3 as a fraction would be square root of 3 over 1. So if I draw my right triangle, that would mean that the opposite side would be square root of 3, the adjacent side would be 1, and to find the other side, you should hopefully recognize this as a special right triangle, but just in case you didn't, this would be 1 square root of 3, and then the hypotenuse would have to be 2. And so this is a 30, 60, 90 triangle, which you've seen in other math courses like Algebra 1, Algebra 2, or Trig, or college algebra. And so what would the theta be here across from the square root of 3? Well, that should be a 60-degree angle. Okay, and since this is positive and the tangent domain has to be between negative pi over 2 and positive pi over 2, if I want positive square root of 3 over 2, it's going to have to be in the first quadrant. Do you remember the little acronym to help us remember which trig functions are positive when? All students take calculus. All trig functions are positive in the first quadrant. Sine is positive in the second. Tangent is positive in the third and in the first, obviously. And cosine is the positive one in the fourth quadrant. So in this case, since I'm between just the fourth and the first quadrant, we just want 60 degrees or pi over 3. I should tell you that the AP Calculus exam only uses radians. You'll almost, actually I'm just going to go ahead and say it, you will never see degrees on the AP Calculus exam that I know of. And I could be mistaken, but I'm willing to say never. So we're never going to use degrees except kind of in a way when I'm instructing you and going back and forth between radians and degrees. So arc sine of 0.3. Now you have to be clever here and understand that 0.3 is actually a fraction. It's a rational number. It's 3/10. 3 over 10. Okay, so if I draw a triangle, I would have the arc sine of 3/10, and that would be 3 on the opposite and 10 on the adjacent. And I'm wondering what angle theta would get me 3 over 10. Okay, this one I don't think you could do without a calculator, so maybe I should not have had this example in here. And maybe I'm just forgetting it right now as I'm making this video because I am a little bit tired. But we're just going to go ahead and skip this one because I think you need a calculator to get it. And to use a calculator to get this, you take sine inverse. There's a button on your calculator, and you just type in 0.3, and it should spit out a angle for you. So we'll go ahead to the next one. And so we have a right angle, and I want the arc cosine of negative 1/2, and that's going to be the adjacent over the hypotenuse. And so I want to know what angle, if the hypotenuse is 2, the other leg has to be square root of 3. And since my domain has to be between 0 and 180, or 0 and pi, when is cosine going to be negative 1/2? Well, that's going to be in the second quadrant. And so this triangle would be here with negative 1 there on the x-axis, positive 2 and then square root of 3. So it would be the reference angle for pi over 6 in the third quadrant. And so this is going to be what would that be? Sorry, brain malfunctioning here. So the theta would be, I think, 5 pi over 6. Actually, nope, 5 pi over 3. There it is. Because I know it's going to be 60 degrees here, but in the second quadrant, and so that's going to be 5 pi over 3. Thanks for your patience there. Sorry about that. Solve for x. If I want to solve for x and I have the arctangent of 2x minus 3 equals pi over 4, all you have to do is just take the tangent of both sides of this equation, because if they are really the same number, you can use them as the input of the same function. So I take the tangent of both sides, and I get 2x minus 3, because remember that inverse functions will undo each other, and you're left just with the arguments. And then on the right side, I'll have the tangent of pi over 4. Tangent of 45 degrees, or pi over 4, would be 1 over 1, or just 1. 2x minus 3 equals 1. 2x equals 4. X equals 2. So just a basic reminder of how to solve trigonometric equations using inverse trig functions. Let's find the exact value, draw a triangle to describe the situation. I want the tangent of the inverse cosine, or arc cos, of negative 1/3. So the arc cosine of negative 1/3 indicates that I have a adjacent side of negative 1 and a hypotenuse of 3. Okay? And so what I want to do here is I want to take the tangent of that same angle theta, right? Because whatever comes out of this expression, cosine of negative 1/3, would be the same angle that I'm putting into the function tangent. Now to get this third side, since this is a right triangle, you know that negative 1 squared plus whatever this side is, I'm going to call it x, x squared should equal 3 squared. Oops, that's 3 squared is 9. So I get 1 plus x squared equals 9. X squared equals 8. And so x equals the positive or negative square root of 8. Okay, so that's what this side is going to be right here. Positive or negative square root of 8. So for this one, how do I know whether it's positive or negative? Well, remember that cosine inverse's domain, or sorry, its range rather, would be between negative, or just between 0 and pi. So then I know that the vertical component should always be positive. So I'm just going to use the positive square root of 8 here, because you're always going to be above the x-axis when you take arc cos, or cos inverse. Okay, so then the tangent of that same angle theta in this triangle would be the opposite over the adjacent. So it would be the square root of 8 over negative 1, or in other words, negative 2 square roots of 2, if I simplify the radical. So I basically use the same right triangle to evaluate the other trig ratio of tangent using the side lengths. What is the secant of sine inverse of x over 1? So if I draw the triangle, that would be x over 1. And this third side would be the hypotenuse squared minus the other side squared under the square root. And here's the theta. So if I want secant, secant is the reciprocal. Secant is the reciprocal of cosine. So it's going to be hypotenuse over adjacent. So if I want the secant of this angle, then it would be the hypotenuse over the adjacent side, 1 over 1 minus this x squared as a radical. So 1 over square root of 1 minus x squared. Okay, so that was sort of all review from trig / algebra 2 or college algebra. And now let's just talk about how to find the derivatives. Okay, so there are 6 inverse trig functions, so therefore I have 6 inverse trig rules. And I'm going to tell you right away, the most important ones to know are arcsine and arctangent. These are the most commonly used, and so these are the ones you have to know. You should also know these other ones too, because these are all fair game, but if I had to tell you to memorize any one of these, I'd tell you to memorize the first 2 that I've highlighted there. The other 4 are kind of extra. I want to reemphasize that anytime you take the derivative of a co-function, whether it's the inverse co or the normal co, you have negative derivatives. All right. Now after looking at these formulas, you might be feeling something like this. Like, I'm done. Like, there are too many rules. There are too many derivative formulas in here. I'm out of here. I just want to tell you to resist the urge to give up. Perseverance is key to success in anything that you do. And although it seems impossible, you will end up knowing these by heart. We have another 6 or 7 months to make sure that you know all of these by heart. And I'll make sure to help you prepare for the AP exam adequately. Now, you might be wondering, how on earth did they get these derivatives? And so I'm going to prove one of them for you. I'm going to prove the sine function one right here. So normally, arcsine, or arcsine of something, so let's just say arcsine of x is some function, and we're going to call it y. Y equals arcsine of x. If I were to take the derivative, actually, before I take the derivative, I'm just going to take the sine of both sides of this equation, just like we did in the problem previous to this. I'm going to take the sine of both sides, and I'm going to just get x equals the sine of y. Okay, now I'm going to take the derivative of both sides with respect to x. And so I get cosine of y, but multiplied by dy dx. And if I solve for dy dx, I get 1 over the cosine of y. Now if I draw a triangle, okay, if I draw a triangle, and so the arc sine of x is y, so it's like y over 1, right? And so when I draw this triangle, the opposite side would be y, and the side would be 1. Okay? And so this side right here becomes the square root of 1 squared minus y squared. Right? And if I'm taking the cosine of this angle, it'd be 1 over the square root of 1 minus x squared. Okay? So there's some variable tricks here that we can change here to get this to work. And I'm sorry, we should have used this ratio. That's why it didn't work. The sine of y is equal to x over 1. And so this angle y is right here. And I'm saying that sine of y is x over 1. And so x would go here on the opposite side, and the hypotenuse would be 1. And then the adjacent side would be the square root of 1 minus x squared. And so that's why the cosine of that angle would be the adjacent over the hypotenuse, and so it's 1 over that. And so 1 over the square root of 1 minus x squared over 1 is just 1 over the square root of x, 1 minus x squared. And so you can see here that that is the same formula that we have here, except it's just in the opposite order, or rather instead I have u's instead of x's, because there could be the different u inside of there. So all that to say, we can just use these formulas to take derivatives. Notice that u is equal to 2x. So the derivative with respect to x of arc sine of 2x, or sine inverse of 2x, is equal to the derivative of the inside, which is 2, over 1 minus that 2x squared, which would be 4x squared, all under a radical. Because the formula for arc sine's derivative is u prime over the square root of 1 minus u squared. So I had to square that inside 2x. Arctangent. Now arctangent's slightly different, and so I'm saying that the 3x is equal to the tangent of y, and so here's the angle y, and so I'm saying the tangent of y is 3x over 1, so that'd be 3x over 1, and so then when I'm taking the derivative of this thing, I take the derivative of both sides, I get 3 equals, and then it's going to be secant squared of y dy dx, and then I have 3 over secant squared of y equals dy dx. And so then I take the secant squared of y. Well, secant of y would be the hypotenuse over the adjacent, and so the hypotenuse is going to be the square root of 1 squared plus 3x squared by the Pythagorean theorem. So it's going to be the square root of 1 plus 9x squared. And so it's 3 over, and secant is going to be the hypotenuse, 1 plus 9x squared, over the adjacent, which is 1. So ends up being 3 over 1 plus 9x squared. Now I'm going to compare that to my table. U prime over 1 plus u squared. I forgot to square this down here, didn't I? It's secant squared. So when I square that, it becomes 3 over 1 plus 9x squared. If I were to just use the table, which I'm going to recommend in the future that you do, it'd just be u prime 3 over 1 plus u squared. And hopefully you can see where I'm getting these formulas from. It's just from using the right triangle trig and the Pythagorean theorem. So that is the derivative of arctangent of 3x. Now this time I'm just going to use the formula, okay? The derivative with respect to x of arctan of u is equal to u prime over 1 plus u squared. So u prime would be 1 half u to the negative 1 half, or rather x to the negative 1 half, sorry about that, all divided by 1 plus u, which is square root of x squared, 1 plus x. So I have to simplify this, and it becomes 1 over 2 square roots of x over 1 plus x. And instead of dividing by 1 plus x, I can have 1 over 2 square root of x times 1 over 1 plus x. And I get 1 over 2 square root of x times 1 plus x. And I can just leave it just like that. Some people will distribute that and that'd be fine, but I'm not. Arc secant of e to the 2x. Now, I'm not going to go through and derive this with the right triangle like I did for some of the other examples. Instead, I'm just going to reference the table. Arc secant is u prime over the absolute value of u times the square root of u squared minus 1, which is a complete nightmare for some of you, but you'll get used to it. Famous things that Lovelace says, you'll get used to the nightmare. So it gets u prime, so it's 2 e to the 2x on top, over the absolute value of u, e to the 2x, times the square root of u squared, which would be e to the 2x squared, plus 1, I think. Let me double check. Minus 1. Of course, I'd be wrong. And then you can just simplify this by having 2 e to the 2x, e to the 2x, absolute value, e to the 4x minus 1. So using the table is just fine, okay? You don't need to derive it every single time. Let's differentiate with respect to the variable x. Y prime would equal u prime, which would be 1, over the square root of 1 minus u squared, plus, and in this case I have to use a product rule, okay? So in this case, I'm going to have left times d right, 1/2, 1 minus x squared raised to the negative 1/2 times the derivative of the inside, which is negative 2x. All right, plus right, 1 minus x squared times d left, which is 1. Simplifying, get 1 over 1 minus x squared. And then I get, looks like x times x is x squared. The negative 2 and the 1/2 will multiply to be negative 1, so I get negative x squared times 1 over the square root of 1 minus x squared plus the square root of 1 minus x squared. So then I get 1 over the square root of 1 minus x squared minus x squared over the square root of 1 minus x squared plus the square root of 1 minus x squared, if I did my math correctly, which I'm hoping I did. And I can get a common denominator for these if I multiply by 1 minus x squared over 1 minus x squared in the radical of a square root here. And so then I get 1 minus x squared plus 1 plus x to the 4th. I'm sorry, that's just going to be 1 minus x squared here, all over square root of 1 minus x squared. So that's going to make 2 minus 2 x squared over the square root of 1 minus x squared. You can factor out that 2. You get 1 plus, or 1 minus x squared rather, all over the square root of 1 minus x squared. And you're going to see them go even further sometimes. This is completely optional at this point, but I'm going to just show you that sometimes it's going to make your life easier if you can recognize this. Divide by the same base, subtract the exponents, so it ends up being 2 times the square root of 1 minus x squared. All right, thank you.